Okay, let's start. Good evening, everyone. I am Shivani Dhok, and I welcome you all for the week 3 tutorial for Modern Digital Communication Techniques course. And so I hope my screen is visible and I am audible clearly. You may stop me at any point and ask questions regarding anything that you want, whatever we are discussing. So again, in this tutorial, we'll first have a recap of week 3 content, followed by some solving examples, which will help you in understanding the concept in a better way, as well as solving your assignment questions. So let's start with recap of week 3 content. So in week 3, the major topics that were covered were variable length coding and sampling. So in variable length coding, the first concept that was introduced was this entropy, which gives the average minimum number of bits required to represent any code. So it is basically an average, which is given by hx, and this hx has a formula as this hx entropy is summation j equal to 1 to m, where m is the number of symbols in that alphabet, pj into Lj, where Pj is the probability with which the jth symbol occurs, and Lj, oh, I'm sorry, this is Pj into log of 1 by Pj, where this Pj is probability of occurrence of jth symbol, where this alphabet is given by A1, A2 until Am. And if we are trying to represent it in terms of bits without loss of generality, this will be to the base 2. So every time when we'll solve this, we'll use base 2, log to the base 2, because we'll be playing with bits. Next thing that was introduced was the minimum length of any code book lies between the entropy and the quantity entropy plus 1. Now suppose I have two random variables x and y, and they are independent, then the joint entropy h of xy is simply hx plus hy. Next, the concept of fixed to variable length coding was introduced. So in this, suppose a source has a symbol ABC, A1, A2, A3, and so on, and one symbol is transmitted at a time generally. But now for what is done is we construct a super symbol which consists of n symbols from this alphabet, and then we do a variable length coding over it. So how does this help? This helps us because this minimum length lies between entropy of x original and entropy of x plus 1 by n. So asymptotically, when the block length n tends to infinity, this average length, minimum average length per symbol tends to the entropy, which is the minimum number of average minimum number of bits required to represent any symbol, any code book. Next thing that was introduced was sampling. So this sampling is somewhat an important concept, because right now when I'm speaking, my vocal cords are vibrating and they are generating an analog signal. It is a continuous in time and continuous in what do we say, continuous in time and continuous in amplitude signal. It is a pure analog signal. But now when I'm speaking this has a microphone which goes to some sort of processor. Now the processor which is going to process it is a digital processor. It is a discrete time processor. So what it does is it first samples that signal into this in time. After that, it will quantize it in multiple levels, finite number of levels. So the first thing is discrete time, making the analog signal discrete in time. That is, if I have an analog signal like this, so what sampling does is it creates a samples like this. Now if I am doing uniform sampling, then I'll sample the signal after every t duration. That is, this is 0, this is t, this is 2t, and so on. So if x of at is the analog signal, if this xat is analog signal, then the sampled version is given by xn, which is constructed as xa at nth t. That is, at every nth, after every nth t time instant, whatever analog value comes, that I'll save as x of n. This is known as the discrete time version of the signal obtained after sampling, where this n is an integer and t is known as the sampling duration. Now the quantity 1 by t, 1 over t, is known as sampling frequency, and choosing this sampling frequency wisely is very important, because when you are hearing it, again you are able to hear an analog signal, which means I need to reconstruct back the analog signal at the receiver end, so that I am able to hear whatever I am speaking. It's the same thing in my voice only. So that reconstruction should be done possibly, and this reconstruction is possible only when the sampling frequency is greater than or equal to twice the maximum frequency which is present in that signal. That is, if this analog signal xat has a maximum frequency of f max, then the sampling frequency should be at least uh, 2 times f max. If it is greater than that, it's okay. So if in that situation I am able to reconstruct back the original signal using this interpolation filter, which reduces to this formula here. This is nothing but simple convolution. Now a detailed derivation of this can be easily found in any of the signals and systems books. I encourage you all to just go through this derivation once. It will be very helpful in understanding these concepts in a better. So these were the two major topics that were introduced in this week. So if anyone has any doubt in these, please let me know. Okay, if there is no doubt, then let's start with the questions. So this is the first question that we have here. It says that find the entropy of the source with probabilities 1 by 5, 1 by 5, 2 by 5, 1 by 10, and 1 by 10. So let's say this is some source x and we need to find the entropy hx. We need to find the value hx, and we have seen that the formula for this is summation j equal to 1 to n. Here n is 1 2 3 4 5, so it will be 1 to 5. Okay, so someone is having a doubt. He says that I have a doubt on prefix free code. Please elaborate it. Okay, so let me do that before starting with questions so that it's easy. I'll just add a page after this, an empty page. Yeah, okay. Okay, so let me start with it in a simple way. So let's say I am having a string 10101111. This is a binary string. This is not a code, just a string. So what does a prefix mean? Anything. So suppose I'm looking at this part here. So anything before that is prefix free, is known as a prefix. That is, this 0 is prefix of this 1. This 0 1 is prefix of the remaining part. So basically any substring of this string which appears at the beginning is a prefix of that particular string. Now it is said that if I have a prefix free code, then I will be able to uniformly decode it. So why is it? So what does prefix free code mean? So let me take a simple example. What I have is, let's say one code is 0, C1 is 0, C2 is 1, and C3 is 0, 1. Okay. Now if you observe here, this is one code. This is a code word. Okay. So this C1 is one code word, this C2 is another code word, and this C3 is the third code word. Now if you observe this C1 is 0, which appears here, which means that this 0 which is equal to C1, this implies that C1 is prefix of C3. Now what is the problem? I have three separate codes, right? So it's okay now. I have one-to-one correspondence between all of these three codes. What is the issue? I can have this, I'll transmit this. So let's say I'll transmit something like this: C1, C2, C3. So what I'm getting here is, what the receiver will see after proper decoding will be, or after proper getting this, recovering back this binary string, will be C1 is 0, C2 is 1, and C3 is 0, 1. So let's say this is, I am transmitting at time t1. Now suppose at time t2, I am transmitting C3, C1, and C2. Now again, what will the receiver see? The C3 is 0, 1, this C1 is 0, and this C2 is 1. Now in both of these cases, receiver will see same binary string. Now in both of these cases, I am receiving same string. So how will the receiver be able to decide whether I am transmitting C1, C2, C3 or C3, C1, C2? Or irrespective of that, if I transmit C3 only, which is 0, 1, how will the receiver decide whether it is C3 or it is a C1 and after that C2? Since the C1 is a prefix of this C3, this decodability goes away. So if I don't have such situation, then I can easily decode what I am transmitting. For example, if I have a code something like this is 0, C2 is 1, 0, and C3 is 1, 1. Now what will happen is, let's say I'm transmitting C1, C2, C3 again. So this will be 0, 1, 0, and 1, 1. Now this code book will be known at the receiver also. And again, this 0 is a single binary digit, and remaining both are 2-bit codes. Now this 0 is not available at any of these initial places, which means that the C1 is not a prefix of C2 and C3. So now what will happen is, this receiver will see a 0. This receiver will see a 0, and it will know that only one such code word occurs which has 0 in its first place, which means this it will directly decode to C1. Next it will see 1. Then it knows that there are two possibilities. So then it will see the second place, that is 0. Now it knows that 1 and 0 together combined will form C2. Now after that, when it goes to 1, again it will know that there is two code words which have 1 at its first place, that is at its MSB. Then it will again wait for the next symbol, next bit, and when it sees 1, now it will be confirmed that it has transmitted C3. But here what will happen is, it will get confused. Like the 0 itself is a symbol, the 0, 1 also, the 0 itself is a code, the 0, 1 is also code. So I won't be able to decode it. So in order to have this uniform decodability, my code should be prefix free. That is one code word, in which case, so you are asking is, so is what if we have C1 C2 C1 C3? For the first case,
No, for the second case, for the prefix free code one.
so what you are asking is C1 C2 C1 C3. So it will be 0,
Yes.
then 1 0, then 0, and then 1 1. It will look bit by bit. It will see 0. It knows that there is a symbol which corresponds to it. So it will decode it as C1. Then it will go to the next bit. It sees a 1. Now again, 1 is not a symbol here. So then it will go to the next bit. So it will look at both of these and see if there is any symbol like this. So yes, there is a symbol which is C2. Then it will go to the fourth bit. It is 0. Again, there is only one code word which corresponds to 0. It will decode it as C1. Now then it will go at the fifth bit. It is 1. It knows that there are two code words which have 1 at its MSB. So it will wait for one more bit. So it will wait and then see it is 1. So now the bit string that it will look at is 1 1. And it knows that this 1 1 corresponds to C3.
Okay, got it. Thank you.
Yeah. Any other doubt? Abhishek, is this clear to you? Prefix free code?
Yes, ma'am.
Yeah, okay, thanks. So, if it's clear, then let's start with questions. Do you have any other doubts? Please let me know.
Ma'am, in discrete memoryless source,
Hmm.
uh, SAT derived that LJ equals to K. If PJ equals to 2 to the power K is a positive integer, therefore LJ equals to K. What does it mean?
Can you repeat?
In the discrete memoryless source, in the lecture, SAT derived that uh, for a code word for a code word A1 A2 to AM, uh, if Pj probability of Pj is 2 to the power minus k, where k is a positive integer, therefore Lj equals to k.
Hmm.
What does it mean? How it is length equals to k? Uh,
Okay.
I
So,
does not
have you
understand.
understood this derivation?
Yeah.
Have you understood this part? Hello?
Yes, ma'am.
Yeah, so this was formed like, okay, from where did this come? So basically, we wanted to look at average length, minimum average length, right? That is, this L bar was summation j equal to 1 to m Lj Pj, and we wanted to minimize this subject to Kraft inequality. That is, j equal to 1 to m 2 to the power minus Lj should be less than or equal to 1. This was the optimization problem which was solved, and this was solved using Lagrange method. Now when we solve it using Lagrange method, first of all, this Lj should be an integer. Your length can't be some 0.5 or that kind of value. Like your length can't be 1.25. As a physical quantity, you can't say you are transmitting zero point 0.1 bit, zero point 0.5 bit. It should be an integer value. So
Ma'am, it is real value only. It is real value. It should be integer or it it uh, it is not fraction value.
Which? This LJ?
This LJ, it is real value, and if we take it fraction 1.25, then what it is not considered.
See. Okay, if I'm transmitting a code word which is which constitutes bits, what do you mean by I have 2.5 bit length code word?
It is the ceiling function 3. Lj equals to 3.
Yeah, but why are you using a ceiling function? Because 2.5 does not make sense.
Yeah.
So you
Yes, yes.
want to send the length should be an integer value. If it is coming as 2.5, I can't transmit it using 2 bits. I need to transmit it with minimum 2.5, means the nearest higher integer. That's why I am using a ceiling operation, right?
Yes.
And this is not ln, this is log to the base 2, right? So when this optimization problem was solved, the actual solution for this LJ opt, that was log 1 1 by pj to the base 2. This was the actual solution, but this may lead to some fractional value, that is some real value. So in order to have it as a integer, we use ceiling operation, right?
Yes, ma'am.
Now if this probability is of the form 2 to the power minus k, that is, let's say it is something like this: 1 by 2, 1 by 4, 1 by 4. Suppose I have symbols like this. So all of these are of the form 2 to the power minus k. Is this fine?
Yeah.
Now using this optimal value, this problem which is given here, whatever we have obtained here, log to the base to 1 by pj, if I use this lj opt as this log to the base to 2 to the power minus k, or rather 1 by 2 to the power minus k, you'll get it something like this,
Yes.
where this k here is an integer, real integer, positive integer. 1 upon 2 to the power 1, 1 upon 2 to the power 2, 1 upon 2 to the power 2. It is a integer, positive integer. So if this I am getting, this I can write as log 2 to the power k to the base 2. Now using the property of logarithm, this becomes k times log.
Yes, ma'am. I understand. Yes, ma'am. Understand.
Okay, so now this log 2 to the base 2 becomes 1, and this is 2. Now this 2 is anyway an integer, so this is just 2. So if I have a symbol with probability of this form, then this k itself will be the length of its code word. I hope this is clear. We'll see an example of this.
Okay, ma'am. Yeah. Yes, ma'am.
Okay. Any other doubt? Okay. So let's start with today's questions session. So what is asked is we need to find the entropy of the source with probabilities 1 by 5, 1 by 5, 2 by 5, 1 by 10 and 1 by 10. So the entropy formula says it is summation over j equal to 1 to 5 pj log to the base to 1 by pj. So using this formula, what do we have here is 1 by 5 into log to the base 2, 1 upon 1 by 5, let me write it once, plus 1 by 5 log to the base 2, 1 divided by 1 by 5, plus 2 by 5 log to the base 2, 1 divided by 2 by 5, plus 1 by 10 log to the base 2, 1 divided by 1 by 10, plus 1 by 10, log to the base 2 1 divided by 1 by 10. So this I can write as this term, these two terms are same, so I can write it as 2 into 1 by 5 into log to the base 2 5 plus 2 by 5 into log to the base 2 5 by 2 plus, again these two terms are same, so this becomes 1 by 10 log to the base 2 10 into 2. Now if you'll have to use your scientific calculator for this, so it is seen that if you use your calculators, then we have log to the base 2 log 5 to the base 2 as 2.32, log 5 by 2 to the base 2 as 1.32, and log 10 to the base 2 as 3.32. And if you solve this entire thing after substitution comes out to be 2.1219 bits. So this is HX. Any questions? Okay, if not, then let's go to the next question. So what it says is, a fair coin is tossed until first head occurs. Let X denote the number of tosses required, and we need to find the uncertainty in X. Now what it says is, a fair coin is tossed. What does this mean? A fair coin means probability of occurrence of head is equal to probability of occurrence of tail is equal to 1 by 2, which means it's a proper coin, like the probability of head and tail is same. Whenever you toss it, anything can happen. It is not biased towards a head or a tail, which means it is probability of head equal to probability of tail equal to half. So what it says is, I am going to toss a coin till the point I observes the first head. Like I tossed a coin, I observed a head, I'll stop. If I toss a coin, I observe a tail, I'll again toss a coin, again I observe the tail, and so on till the point I observe a observe a head. So what are the possibilities? So this random variable X, what does it say? It denotes the number of tosses required to see a head. So what are the possible values that X can take? So it may happen that X this X can take a value, X can be 1, that is at very first head, for very first toss I am able to see a head. So at first toss is itself I am able to see a head, and what is the probability of that? Probability of that is equal to probability of seeing a head, which is 1 by 2. Suppose it happens like this. So this is head. Okay. Now this may happen that first I observed a tail, and at second toss I observed a head, which means my X is 2. Now here this tail, this occurs with a probability of half, and this head occurs with a probability of half, which means that this is 1 by 2 into 1 by 2, which I can write as 1 upon 2 square. Now suppose this occurs, TTH, that is after third toss. At third toss I observed a head. So here this tail will be coming at a probability half, again half and half. So this will be 1 upon 2 to the power 3. Now so on, let's say x is n. That is, at nth toss I am able to see a head. That is, I'll see tails. This will be n minus 1 times. And then I'll see a head. So each of this tail will occur at a probability of half. That is, and this head will occur at a probability half. So this will be 1 by 2 into 1 by 2 into 1 by 2 and so on n times. So this will be 1 upon 2 to the power n, and this will continue, this possibility will continue infinite number of times. This n will take a value from 1, 2, 3, 4 and so on. Okay, so in general, probability that x takes a value n is given by 1 upon 2 to the power n. And what we need to find is, we need to find this h of x. This h of x will be, how many values does this x take? X takes a value from 1, 2, 3, 4 till infinity, all the natural numbers. So this summation will be from n equal to 1 to infinity. Probability of x into log of 1 by probability of x, and this is with a base 2. So this I can write as summation n equal to 1 to infinity probability of, okay, let me be a bit precise. Let me write it, probability that x takes a value n into log of 1 by probability that x takes a value n to the base 2, and we know that this is n equal to 1 to infinity. Probability that x takes a value n is 1 upon 2 to the power n. So this is 1 by 2 to the power n into log 1 upon 1 by 2 to the power n. So this reduces to summation n equal to 1 to infinity 1 by 2 to the power n into log 2 to the power n. This is equal to summation n equal to 1 to infinity n into 1 by 2 to the power n into log 2 to the base 2, which is equal to 1. So basically this factor here is n into log 2 to the base 2, and this term is equal to 1. So this is what we are having right now. Now this is an infinite arithmetic IGP, infinite and arithmetic geometric progression. So let's say what we are having here is this hx. I keep on forgetting this formula for series, so instead of remembering formula I prefer going with this simple method. So this hx I can write as 1 into 1 by 2 plus 2 into 1 by 2 square plus 3 into 1 by 2 cube and so on. Now I'll take half hx, which comes out to be 1 into 1 by 2 square plus 2 into 1 by 2 square 1 by 2 cube and so on, and I'll subtract this. So what I have here is half hx, which is equal to 1 by 2 plus 1 by 2 square and so on, which is again a simple IGP which takes the form of first term upon 1 minus ratio, common ratio, which comes out to be 1, which means that this hx is equal to 2 bits. Any questions, any doubts in this particular question?
Ma'am, get back to previous slide once. Okay, ma'am.
Okay.
Okay, ma'am.
Yeah. Don't worry, all of this is available on your NPTEL. Like these notes with solutions are available on your NPTEL platform in tutorial section. You can go to the tutorial section there, and
Okay.
at very bottom in that you will be directed to a Google link. In that you will have all of these scripts and also YouTube links to this particular lecture, which I'll upload after this session ends. So everything will be available to you. So don't worry. Okay, so if there are no questions, then let's move on to the third one. So what we have here is, let x and y be independent discrete sources with symbol probabilities given by the sets this one and this one. Okay, and we need to find this joint entropy h of x comma y. Now it was discussed in the lecture that h of xy is equal to h of x plus h of y if x and y are independent. Okay, so we need to find this. So in order to find this, let us first find out what is h of x. So this h of x is simply summation j equal to 1 to, for this x set x, this is the set of probabilities, that is it has 4 values. 4 log of 1 by pj into pj, which is equal to, now it has same probability, so I can write it as 1 by 4 into log of 1 divided by 1 by 4 into 4, because it is the same thing getting repeated 4 times. So this I can write as log to the base 2 4, which is equal to log of 2 square by 2, which is 2 times log 2 to the base 2, which is equal to 2 bits. Now let us take h of y, which is summation j equal to 1 to 4 log, sorry, not 4. Here I have 1 2 3 4 5 6, so this will be summation j equal to 1 to 6 pj log of 1 by pj, and this comes out to be 1 by 4 into log of 1 upon 1 by 4, which is 4, plus 1 by 16 into log of 1 upon 1 by 16, so this is 16. Now this term 1 by 16 into log 16 is repeated 1 2 3 4 times, so I can simply write it as 4, and plus 1 by 2 into log of 1 upon 1 by 2, which is 2. Okay, so let me take this to the next page. So this is what we are having. Now this I can write as 1 by 4 into log of 2 square, plus this 4 by 16 comes out to be 1 by 4 into log of 2 to the power 4, plus 1 by log 2 to the base 2 is simply 1, so this comes out to be 1 by 2. Now this is equal to 2 by 4 plus 4 by 4 plus 1 by 2, which is equal to 1 by 2 plus 1 by 2 plus 1, which is equal to 2 bits. And therefore h of xy is equal to h of x plus h of y, which comes out to be 2. This was 2 plus 2, which is equal to 4 bits. Any question? Okay, if not, then let's go ahead with the next question that we are having here. So it says that consider an IIT source, symbols xi, and the PMF for it is given as 1 by 4, 1 by 4, 1 by 8, 1 by 8, 1 by 8, 1 by 8. Okay, and what we need to find is, we need to find this joint entropy of h of x1, x2, x3 till xn. Now what it is given is these xi's. These xi's are IIT. And we have seen here that if two random variables are independent, then their joint entropy is simply summation of their two entropies. So it says, so if I have it in this form, it is hx equal to hx1. If I have this hx1, x2, x3 until xn, and if they are IID, that is independent and identically distributed, so this I can simply write as h of x1 plus h of x2 and so on till h of xn. And another thing is, these all are IID, so these will lead to simply like this h of x2 will be equal to h of x1 and so on. So this I can write as n times h of x1. Okay, so this is the first thing that we are having here. And next what we need to find is, what is this h of x1? So this h of x1 is given by summation j equal to 1 to, how many symbols do we have? So it is 3 plus 3, 6. So j equal to 1 to 6 pj into log of 1 by pj. So this comes out to be 1 by 4 into log of 1 divided by 1 by 4 plus 1 by 4 into log of 1 upon 1 by 4 plus 1 by 8 into log of 1 upon 1 by 8 plus 1 by 8 into log of 1 upon 1 by 8 plus 1 by 8 into log of 1 upon 1 by 8 plus 1 by 8 into log of 1 upon 1 by 8. So what do we have is 2 times 1 by 4 into log of 2 square plus 4 times 1 by 8 into log of 2 cube. So this comes out to be 2 by 4 into 2 plus this is 2, so this will be 3 by 2. So what we have is 5 by 2, which comes out to be 2.5 bits. And therefore this joint entropy h of x1 till xn is simply 2.5 times n bits. I hope this part is clear. Any questions? Okay, if there are no questions, then let's go ahead with this. So I think this question will help you understand more, Abhishek, regarding that LJ thing. LJ is some log of, like the probability PJ is some log, some to the power minus k. It is of that form. So in this question, what do we need to do is we need to construct a prefix-free code with LJ as log 1 by pj to the base 2 for symbols with probability these. And next we need to find an average length, the average length of the code, and we need to compare the same with the fixed length code and Huffman code. So first what we need to do is we need to construct a prefix-free code. So for that, what we'll do is we'll first find the lengths and then construct a binary tree to find a prefix-free code for each of these symbols, uh, which and the code words will be located at the leaf nodes. This will be the process that we'll follow. After that, we'll find the average length of the code and we'll compare it with the fixed length coding. Then we'll apply the Huffman algorithm in order to find the code word, and then we'll compare the length of the same with all of these two. One more thing we'll do, we'll find the entropy also in order to understand what exactly is happening and how much close we are to the minimum possible length. Okay, so let's start with the first part. Let me highlight the part which we are going to do first. So first we will be doing construction of prefix free code with his probabilities. Okay, so let's start. What we are having here is L1 is 1 by 8. I'm sorry, this P1 is 1 by 8, which means that this L1 is CL function of log to the base 2 1 divided by 1 by 8. This I can write as CL function of log 2 cube to the base 2, which is simply 3 bits. Similarly, if I have this P2, I'll have this 1 by 8, which means this L2 is log to the base 2 1 divided by 1 by 8. Now again this will be simply 3 bits. Next what we have is P3, which is 1 by 4. This implies the L3 will be CL function log to the base 2 1 divided by 1 by 4, which is equal to CL of log of 2 square to the base 2, which is equal to 2 bits. And P4 is 1 by 2, which implies that L4 is log to the base 2 1 divided by 1 by 2, which is CL of log 2 to the base 2, which is simply 1 bit. So what do we have is we have 3 bits, 3 bits, 2 bits and 1 bit. These are the lengths that we are having here. So now let us try to construct a binary tree. So what do we have is we have one code word of length 1. So let's say this is the code word of length 1, and let's say this is 1 0. Okay, this is 1 0, and then we have one code of 2 bits. So let's extend this like this. Okay, so let's say this is the second code word that we are having, which is of length 2. So basically the first code word is this. Let me write it as 1, and this is equal to C4. The second code word is 0 1, which is of 2 bits. So this is 0 1, this is C3, and then we have another code words of 3 and 3 bits. So I'll extend this again like this. So what do we have is, let's see, this is 0 0, let me label it, this is 1 0 and 1 0. So this is 0 0 1, this is C2, and what we have here is 0 0 0, which is C1. Okay. So what we are having here is the lengths. The lengths are 3 3 2 1. So this is the set for LJs, and the probability set is 1 by 8, 1 by 8, 1 by 4, and 1 by 2. This is the set for PJs. And next what we need to do is, we need to find the average length of the code. Okay, so what do we have is, we need to find this L bar, which is simply J equal to 1 to 4 LJ PJ. Okay, so this comes out to be 3 into 1 by 8 plus 3 into 1 by 8 plus 2 into 1 by 4 plus 1 into 1 by 4. Okay, so this is basically 3 by 4. So this is 1 by 2. This is 3 by 4 plus 2 by 4, that is 1 by 2 plus 1 by 2, which is 1 plus 0.75, which is equal to 1.75 bits. This is the average length. Now how many symbols do we have? So we need to compare this with fixed length code. So if I need to go for fixed length code, so for fixed length code, what is the value of m? M is 4, which means that the number of bits, that is this L, will be basically log m to the base 2 with a ceiling function, which is simply C log of 4 to the base 2, which is simply 2 bits. So this is what we are having here. Now another thing that you need to observe is this 1 by 8 I can write as 2 to the power minus 3. This is also 2 to the power minus 3. This is 2 to the power minus 1, and this is 2 to the power minus 1. This is 2 to the power minus 2, sorry. So again, if you observe carefully, what your doubt was, this 3 and this 3 is same. We have this 3 and this 3. Similarly, I have this 2 and this 2, and I have this 1 and this 1. So if the probabilities are of the form 2 to the power minus k, where this k is some positive integer, then in that situation the length will be simply k. This is what we are getting here. But is this an optimum length, or is this the best length? Let us check. But before that, what we'll do is, we'll see if the what does this Huffman code have to give us. So next thing that we need to do is, we need to look what this Huffman code is trying to give us. So how do we construct a Huffman code? So basically, we arrange these probabilities like this in decreasing order, that will arrange. And then what we need to do is, from this set we need to take the two least probabilities and combine them. So we need to combine the least two like this and form one symbol. So we need to combine these two and form one symbol, and this symbol will be basically of probability 1 by 4. We need to add them, 1 by 8 plus 1 by 8, that is 1 by 4. So this is what we are having here. And now the code book becomes something like this. So we have 1 by, let me write it here, this is 1 by 4, this is 1 by 4 and 1 by 2. Then again we need to combine the two symbols which are having the least probability. So here it is 1 by 4 and 1 by 4. So we need to combine these two, something like this. So this is what we are having, and these two will form one symbol and its probability will be 1 by 2. And now we have another symbol of probability 1 by 2. We'll carry it like this. This is the only thing that is remaining. So we'll combine these two like this. And now we'll give the labels 1 0 1 0 1 0. And if that is the case, you need to observe carefully. This is forming a binary tree. Now this is a binary tree where this is a leaf node, this is a leaf node, this is a leaf node, and this is a leaf node. Now this leaf node corresponds to this symbol C1. This leaf node corresponds to symbol C2. This leaf node corresponds to symbol C3. I'm sorry, this is opposite. Extremely sorry. Yeah. So this leaf node here corresponds to symbol C1, this one. Then this leaf node here corresponds to symbol C2, which is this. This one is the leaf node corresponding to C3, and this one is the leaf node. This one is the leaf node corresponding to C4. This is simple binary tree. So if I reconstruct it, it looks something like this. This is C4 with 1 0. Then again this is extended. This is C3. Again this is 1 0. And then this is extended further like this. This is C2 and this is C1 and this is 1 0 again. I'll just take this tree here. So if you observe carefully here, what is the code word for C1? So the C1 has a code word 0 0 0. Same thing you can observe here. It is 0 0 0. So it is simply 0 0 0. Then for C2, what do we have? 0 0 1. So it is 0 0 1. Okay. So this C2 has 0 0 1. Now let us look at C3. It is 0 1. Same thing we have here. It is 0 1. Okay. So this is C3, which is 0 1. And what is your C4? It is simply 1. Same thing. It is simply 1 here. That is C4 is simply 1. So this has a length 3 and its probability is 1 by 8. Similarly, this has 3, 1 by 8. This is 2, 1 by 4, and it is of length 1, which is 1 by 2. And if you observe carefully, this is exactly what we have obtained for this particular case of Lj as log to the base to 1 by Pj. So again, for this Huffman code, L bar for Huffman comes out to be exactly same as 1.75 bits. Okay, so now just for comparison purpose, it's not asked in the question, still we'll find out what is this hx. So this hx will be simply summation j equal to 1 to 4 pj log to the base to 1 by pj. So this comes out to be 1 by 8 log to the base to 1 upon 1 by 8 plus 1 by 8 into log to the base to 1 divided by 1 by 8 plus 1 by 4 log to the base to 1 upon 1 by 4 plus 1 by 2 log to the base to 1 divided by 1 by 2. So this comes out to be 1 by 8 into log 8, which is log 2 cube, which is 3, plus 1 by 8 into 3 plus 1 by 4, this is log 4, which is log 2 square, which is 2, plus 1 by 2, this is simply log 2 into 1. And again, this is the same equation that we had seen here. So again, this is also 1.75 bits. Okay, so now if you observe carefully, this hx is equal to L bar min, or rather L bar of Huffman, which is equal to L bar min, which we had obtained using that Lj formula. Okay, so using this construction that we had done here, we were getting 1.75 bits. Even the Huffman is giving me the same thing, that is 1.75 bits, and even the entropy is also 1.75 bits. Now what exactly is happening here? So if we go back to our discussion which we did at the beginning of our class, this one, so where we were trying to find the minimum average length of this particular um of any code. So basically we had to minimize this quantity with respect to the craft inequality constraint. This was the optimization problem which we are solving, and this Lj optimum was obtained as, in real case, was obtained as log to the base to 1 by pj. This was the solution that that was obtained, and this value is taken as it is when this pj takes this form of 2 to the power minus k. Now if that is the case and all my probabilities are of this form, then the formula, this Lj optimum, will give me the least possible minimum, or the best possible, or rather will lead to this the optimal value which we had obtained from the which we had obtained from this solution here, the solution of this optimization problem. And the question that we had considered right now was exactly of that form. So these lengths, these were of the form of 2 to the power minus k, and therefore these led to the optimal solution, the minimum possible length, which is given by the formula of this entropy, that is 1.75 bits. Same thing. And even this Huffman tries to create a tree which allocates the minimum possible bits. So that is what we are getting here. So this Huffman, the code given by this Huffman and that we had obtained from this construction of tree is exactly the same. Rather, this tree and this tree is same thing. So when I'm having the probabilities in this form, I'm going to get the best possible code with the minimum possible length which is given by this entropy value. Any questions? Okay, if okay, so if there are no questions, then let's see what happens if this probability is not of the form of 2 to the power minus k. That is, what we need to do is we need to repeat the question 5 for symbol probabilities 1 by 6, 1 by 6 and 4 by 6. So what all was asked in question 1? So first what we need to do is, first thing we'll do is construct a code with Lj as ceiling of log to the base 2 1 by Pj. So in that case, what we have is, we have this P1 as 1 by 6, which means L1 is log to the base 2, or ceiling of log to the base 2 1 divided by 1 by 6, which is log to the base 2 6, which comes out to be seal of 2.584, which is 3 bits. Then P2 is again 1 by 6, which means that this L2, which is log to the base 2 1 divided by 1 by 6, this is again 3 bits. And this P3 is 4 by 6, which means that this L3 is log to the base 2 1 divided by 4 by 6, which is seal of log of 6 by 4 to the base 2, which is ceiling of 0.584. So this comes out to be 1 bit. So what do we have here is L1 is of 3 bits, L3 is 3 bits, and L1 and L2 are of 3 bits, and L3 is of 1 bit. So again we'll try to construct a tree for this. So what do we have here is, this is L1. This is the first thing that we are having, 1 0. We have one code word of length 1, so let's say it lies here. So this is C3. Then we have two code words of length 3. So what we can have is, let's say this is not extended and only this part is extended, just something like this. So this will be 1 0. So again this will lead to a 2-bit code. I don't want this, I want a 3-bit. So I'll again extend this something like this. So this will be 1 0. And now I'll get 3-bit codes, which is something like this. Let's say this is C2 and this is C1. So what do we have is, the first 3-bit code is this 0 0 0, which is here. The next 3-bit code is 0 0 1, which is here. And the next 1-bit code is this, which is 1. Okay, now let's find L bar. So the L bar, that is average length, L bar here, let me name it as LJ thing, is summation j equal to 1 to 3 pj lj, which is simply 3 into 1 by 6 plus 3 into 1 by 6 plus 4 into, 1 into 4 by 6. So this comes out to be 10 by 6, which is equal to 1.6667 bits. Now the question is, can we do better? Is there a scope of doing better? So we'll check that. The next, okay, apart from that, if we go for a fixed length code, this is 3 for, so LFLC fixed length is basically log to the base 2 m, which is ceiling, which is log 3 to the base 2 seal. So this comes out to be 2 bits. Okay, so now this is LJ, which is for variable length code. LFLC is for fixed length code is 2 bits. Okay, we are doing little bit better than fixed length coding, but can we do better? So let's check what is the entropy for this. So the entropy for this will be summation j equal to 1 to 3 pj into log of 1 by pj. Now this comes out to be 1 by 6 into log to the base 2 of 1 upon 1 by 6, this is 6, plus 1 by 6 into log to the base 2 6, plus 4 by 6 into log to the base 2 6 by 4. Okay, now if I solve this, this comes out to be 2 into 1 by 6 into log 6 we have found out as 2.584, plus this 4 by 6 into log 6 by 4 we had found out as 0.584, and this comes out to be approximately 1.25 bits. Approximately, this is not exact, it will have more decimals here. So this is entropy, and this is what we had obtained, 1.6667, and this is 1.25. So basically we are consuming more average on an average more bits compared to this hx. So let's check if Huffman code helps. So the question that we need to check is, can Huffman algorithm help improving Elmin? So let us try to do Huffman here. So again we'll arrange it in decreasing order, something like this. So this will be 4 by 6, 1 by 6 and 1 by 6. So we'll combine the least probability thing like this and take it in one symbol. So this symbol will have probability 1 by 6 plus 1 by 6, that is 2 by 6 here. Then again take this here, which is 4 by 6, and these are the only two symbols that are remaining. So let us combine this, so that will lead to 4 by 6 plus 2 by 6, that is 1. So this is what we are having here. Let me label it as 1 0 and 1 0. So the 3 leaf nodes that are available here are this one, and this one. Okay, so in order to get a good visualization, the way we are able to visualize a tree, so let's do that. What we are having here is, this tree is exactly same to 1 0. One leaf node is present here, which correspond to probability 4 by 6. Then I have this node branching out into 2, something like this. So this one is also 1 by 6, and this also is 1 by 6, and again this is 1 0. So what we are having here is this C1, okay, C1, C2, C3. Okay, so now this C1 is simply a 2-bit code, 0 0. So the C1 is 0 0. Here 0 0. Similarly, it is 0 0. This C2 is 0 1. It is 0 1. This C2 is 0 1, and this C3 is simply 1. So this is L1, L2, L3, which means that if I need to do Huffman, the minimum length or the length of this code, what I have here is L bar of Huffman is simply L1 is 2, L2 is 2, and L3 is 1. So this is 2 into 1 by 6. Yeah, 2 into 1 by 6 plus 2 into 1 by 6 plus 1 into 4 by 6. So this is 2 plus 2 plus 4, which is 8 by 6, which is simply 1.333 bits. Now this 1.333 bits is less than what we had obtained for this one, Lij, L for Lj, which was 1.6667. Also, this thing is closer to Hx. This thing is closer to Hx. Why? Because earlier the C1, C2 were consuming 3 bits, but now they are consuming only 2 bits. So somewhat this Huffman algorithm is helping us. Another thing to note here is this Lij, this thing that we had obtained is lying between Hx and Hx plus 1. So that thing is also okay. That's not an issue, which was shown or proved in the lecture. So this Huffman algorithm is helping us in reducing the average number of bits and taking us closer to the entropy value. Any questions? Okay, if not, then let us go ahead for the next question, and that is what it says is consider a binary source with probabilities that 0 appears with a probability 0.8 and 1 occurs with a probability of 0.2, and we need to find the minimum average number of bits needed to code it. Okay, and now suppose a new super symbol is created with length 4. That is, the super symbol consists of 4 symbols. Then find the average bits per symbol for this configuration. Okay, so first what we'll do is we'll first do this simple thing. We need to find the minimum average number of bits needed to code it, and we know that this factor here is nothing but entropy, which is Hx, which will be simply probability of 0 into log of 1 by probability of 0 plus probability of 1 into log of 1 upon probability of 1, and this is to the base 2, which is simply 0.8 with a minus sign, log of 0.8 plus 0.2 into log of 0.2, like this. So this is what we are having. Let us try to solve this. So what we are having is we need to find 0.8 into log to the base 2, 0.8 plus 0.2 into log to the base 2 into 0.2. So what it comes as is 0.7219. So what we are having here is this value, and we need to multiply this entire thing by minus sign. So this comes out to be this value here, which is given, that is 0.7219. So this comes out to be 0.7219 bits. Okay, now let us go ahead with the next part of this question. So what it says is, suppose a new super symbol is created of length 4, and we need to find the average bits per symbol for this configuration. Okay, so what it says is, we have created a super symbol with n equal to 4 like this, and we need to find the minimum average number of bits per symbol for this configuration. Okay, so if I have four possibilities, four length symbol, so each of this blank can take two values, which means I have 2 to the power 4, that is 16 possibilities for super symbol. Each of this place can take four each of this each of this place can take either 0 or 1, and that will be total in total 16 possible values. Okay, so those will be 0 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1, and the next set will be 1 0 0 0 1 0 0 1 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. So what are the possibilities? These are the 16 possibilities that we are having here, and each of it will have some probability. Okay, yeah. So the probability for this symbol will be the 0 appears 4 times, so this will be 0 0.4. The 0 comes with probability 0.8 to the power 4, which is simply 0 0.4096. This is 0 0.8 cube into 0 0.2, which is simply 0 0.1024. This is again 0 0.8 cube, 0 appears 3 times into 0 0.2, which is 0 0.1024. Now here it is 0 0.8 square, 0 appears twice into 0 0.2 square, which is 0 0.0256. Then here again 0 appears 3 times, so this is 0 0.8 to the power 3 into 0 0.2, which comes out to be 0 0.1024. Then again we have 0 0.8 square into 0 0.2 square, which is 0 0.0256. Then same thing we are having here. This is 0 0.8 square into 0 0.2 square, which is 0 0.0256, and this is 0 0.8 into 0 0.1 cube, sorry 0 0.2 cube, and this comes out to be 0 0.0064. Similarly here, what do we have is 0 appears 3 times, so 0 0.8 cube into 0 0.2, this is 0.1024. Then this is 0.8 square into 0.2 square. 1 appears twice and 0 also appears twice, so this comes out to be 0.0256. Again we have 0.8 square into 0.2 square, which is 0.0256. Now here what do we have is 3 appears twice and 0 appears once, so this is 0.8 into 0.2 cube, which is equal to 0.0064. Same here, we have 0.8 square into 0.2 square, so this is 0.0256. What we have here is 0.8 into 0.2 cube, which is 0.025, 0.0064, 0.8 into 0.2 cube, which is 0.0064, and 0.2 to the power 4, it's all 1, so this comes out to be 0.0016. Now you observe here this factor appears once, also this factor appears once. Then what do we have is this, okay, I'll use different color, it's not dominant, this factor appears 4 times. Then this factor, this appears total 6 times. Okay, and this factor 0.0064 again appears 4 times. So what do we have here? Let this x tilde be the new symbol, new super symbol. So what do we have here is hx tilde is equal to 0.4096 into log of 1 upon 0.4096 plus this 0.1024 appears 4 times, so this will be 4 into 0.1024 into log of 1 upon 0.1024 plus this 0.0256 appears 6 times, so this will be 6 times 0.0256 into log of 1 upon 0.0256 plus this next factor is 0.0064, this appears 4 times, so this will be 4 into 0.0064 log of 1 by 0.0064 plus the last term is 0.0016, so this is 0.0016 into log 1 upon 0.0016. If you solve this on calculator, what you obtain is 2.8877. Okay, and now this hx tilde by n will be 2.8877 divided by 4. So this comes out to be this comes out to be 0.721925 bits, and which is very close. This is very close to what we have obtained here. So this thing is very close to hx, and this is what we were also observing when we were discussing this variable to fixed variable length coding discussion here. So if we have fixed variable length coding, this hx for the super symbol by, so this thing is something like this. So as this n so what we have is hx, this L min average. So this will be entropy of the super symbol divided by n. This thing is between hx and hx plus 1 by n, and as this n tends to infinity, this L min, that is hx of super symbol by n, this tends to hx, which is the original entropy, if I just transmit one symbol. So this is what we are observing here. So this is 0.7219, and original hx was also 0.7219, which was quite close. So this is what we are observing. So if I increase my n further, this will become more close to the original hx. I hope this is clear. Any questions? Okay, this was all I wanted to cover for variable length coding. The questions after this are for sampling. So as I discussed in the recap of first week, two major things were introduced. One was this entropy and other things that was related to variable length coding, variable length source coding. And now the next part that was introduced was sampling. So the sampling theorem, Nyquist sampling theorem, which said that in order to perfectly reconstruct my original analog signal, the sampling frequency fs should be at least equal to twice the maximum frequency which is present in my signal. So this was a sampling theorem. This is the relation between the sampling frequency and the maximum frequency that is present in the signal. So we'll try to make use of this relation and find the sampling frequency for some common signals and look at some interesting things that happen if we have combination of two signals and or so. So the first question related to sampling is let xt be sine square 2 pi f naught t, and we need to find the sampling frequency for this signal. Now this xt is basically sine square 2 pi f naught t, and this I can write as 1 minus cos 2 into 2 pi f naught t by 2, which is 1 minus cos of 2 pi 2 f naught t by 2. Now observe here this factor, or let me write it like this, 1 by 2, 1 by 2. Observe carefully this factor. This is a DC component. This is a DC component, and frequency for a DC component is 0. So whatever frequency is being contributed is by this factor, and this has frequency as 2f0. So if you try to plot its Fourier spectrum, what we obtain is something like this. So this is f. So I'll have this DC component here, 1 by 2. Okay, and I'll have something here, one impulse here and another impulse here. So the maximum frequency, so this will be located at plus minus 2f0. So the maximum frequency of this signal is 2f0. So what we have here is f max is equal to 2f0, and therefore the minimum sampling frequency is simply 2 times f max. So fs, let's say it is minimum, is 2 times f max, and this comes out to be 2 times 2f0, which is equal to 4f0. Any questions? Okay, if there are no questions, let us look at the next question. So what it says is, if x1t and x2t have Nyquist sampling rate of fs1 and fs2 respectively. So this Nyquist sampling rate is basically the minimum sampling rate for that, which is equal to 2 times f max. Okay, so the Nyquist rate of x1, so this x1 of t has Nyquist rate as fs1, which means that f max 1, or I'll write it as fm 1, will be fs1 by 2. Similarly, this x2t has minimum sampling frequency as fs2, which means that this fm2, that is maximum frequency of this, will be fs2 by 2. Now what we need to do is we need to find the Nyquist sampling rate for y1t, which is x1t convolved with x2t. Now just to recall this convolution operation, that is x1t convolved with x2t, is simply integral minus infinity to infinity x1 tau x2 of t minus tau t tau. This is in time domain, and if we take its frequency domain representation, then it is simply x1 of f into x2 of f. That is, it is pointwise multiplication of these. And what we need to do is we need to find maximum minimum sampling frequency for this. So let's say this fm is maximum frequency in y1t. Okay, and this y1t let's say has a Fourier transform y1 of f, and this y1 of f is simply multiplication of x1 of f and x2 of f. Now let's say we have it something like this. This one is my x1 of f, that is Fourier spectral what we can say, Fourier spectrum of x1t, magnitude to be specific, is something like this. And let's say I have this thing as x2 of f, which means this point is simply fm2, and this is minus fm2, and this point here is fm1, and this point here is minus fm1. Now these two get multiplied pointwise, which means if this part is 0 from here to here like this, then if they are getting multiplied pointwise, the only frequency range that will survive will be this. So for this case fm is basically equal to fm2, which I can write as this is minimum of fm2 comma fm1. Similarly, if I have opposite case, and this is, let's say, fm1 minus fm1, and this is something like this. Okay, so this will be fm2 and minus fm2. This thing is magnitude of x2f, and this thing is magnitude of x1f. Now again, since I'm having pointwise multiplication, then it simply means that the only frequency range that will survive will be this. So in this situation, fm will be equal to fm1, which is again minimum of fm1 and fm2. So in general, what I have is this fm as minimum of fm1 comma fm2. Let me add this page. So what I have is the maximum frequency fm is minimum of fm1 comma fm2. So by Nyquist sampling theorem, minimum sampling frequency is simply fs is 2 times fm, which is 2 times minimum of fm1 comma fm2. This is equal to minimum of 2 times fm1 comma 2 times fm2. Now again, if you observe here, this 2 times fm1 is simply, if you observe here, this 2 times fm1 is simply fs1, and 2 times fm2 is simply fs2. So what we have is, this is equal to minimum of 2 fs1 comma fs. Any questions? Okay, if there are no questions, then I'll go to the next part of this. So the next part is basically this y2t. This y2t is simply x1t into x2t. Now again, we have seen here that this x1t has maximum frequency as this, and x2t has maximum frequency as this, as discussed in the previous part also. That remains same. But now what we are having here is x1t is getting multiplied to x2t, and by the properties of Fourier transform, this is equal to x1 of f convolved with x2 of f. So multiplication in time domain results in convolution in frequency domain. So let's try to understand what is happening here. Yeah. Okay. So let's say this is x1f, and let's say this is x2f, and these two are getting convolved, and this one, this point here is basically fm1, this is minus fm1, this is fm2, this is minus fm2, and what we have here, let's say this is y2 of f. So we want here y2 of f, and this is basically convolution of x1 of f and x2 of f, convolution of these two. So if so what convolution does is it's like flip, shift, multiply and add. So this one, once flipped, shifted and added, that overlap will start from a point which is minus fm1 plus fm2. That is, if you flip this remains same. So the overlap will start at this point somewhere here, like this. So basically this will be the shift that we are having. Sorry, this will be the shift that we'll be having, and this point will be basically minus fm1 plus fm2. And similarly the overlap will end when it is something like this. That is, this point will be fm1 plus fm2. So this thing will be something like this, where this point will be fm1 plus fm2, and this point here, this will be minus fm1 plus fm2. So from this, what we observe here, that the maximum frequency fm is basically fm1 plus fm2. Therefore the sampling frequency fs is simply 2 times fm, which is equal to 2 times fm1 plus fm2, which we can write as 2 times fm1 plus 2 times fm2, and 2 times fm1 is simply fs1 plus this 2 times fm2 is simply fs2. So this is fs. Any doubts here? Okay, if there are no doubts, then let's go to the last question that I want to cover today. So this is a very simple question. So what it says is, consider a voice signal with maximum frequency 3.5 kilohertz. Now a voice signal is an analog signal. So what it says is, I have a signal. This is voice signal. This is voice signal, and this has maximum frequency f max as 3.5 kilohertz. And it is sampled with a sampling frequency of 8 kilo samples per second. Okay, so sampling frequency is given as 8 kilo samples per second. Okay, this is given to us. Okay, now if you observe carefully, f max is 3.5 kilohertz. So the maximum frequency or the minimum sampling frequency, fs min, is basically 3.5 into 2, that is 7 kilo sample per second, or 7 kilohertz. So this fs is obviously greater than 7 kilo samples per second. So this sampling is okay. Sampling is fine with respect to sampling theorem. Okay, now what is asked is, okay, what does the sampling frequency tells us? That in 1 second 8,000 samples are generated. This is what it tells us, that at every second I am having 8,000 samples. Every second I am sampling 8,000 values from that particular voice or particular analog signal. Now what it says is, next thing is, each sample is uniformly sampled to one of the 8 quantization levels. So one sample is quantized to one of 8 quantization levels, uniformly quantized. Now this 8 levels, so if I have 8 values and I need to represent them through bits, so it's like I have m equal to 8 and I need to find L. So basically the number of symbols that I have is 8, and if I go for a fixed length coding, then I need to find what is L. So this L is simply log m to the base 2, which comes out to be log of 2 log of 8 to the base 2, which is simply 3 bits, which means that one sample corresponds to 3 bits. Okay, so what information do we have? In 1 second, 8,000 samples, and one sample is equivalent to 3 bits, which means that what do we need to find is, we need to find this data rate in bits per second. So if in 1 second I have 8,000 samples and one sample corresponds to 3 bits, then this 8,000 samples which are obtained per second are equivalent to 8,000 into 3 bits per second. So this is simply 8 3s are 24. So this is 24,000 bits per second, or this is simply 24 kilobits per second. So this is the data rate that we are obtaining here, the rate at which we are sending. So this is simply 24 kilobits per second. Very simple question, nothing much, no maths involved or no concept involved. It's a simple manipulation. Any questions at this point? This was the last question that I had planned to cover today. If you have questions in any of the things that I discussed today, please feel free to ask. This was all I wanted to cover. And if you have no further questions, you are free to leave the meeting at any time. If you have any questions, you may ask it. A book for practicing more. Okay, so this entropy questions you can find in Thomas and Cover. I think you go to the web page, course web page for this. There are some books referred, listed. I'll just quickly go and post the same on your, 1 second. And just go to the course website and just post it once. But yeah, this entropy based questions you can solve from Thomas and Cover, Elements of Information Theory. And some simple books, very basic initial UG level books. I am just posting them in the chat box. You can refer them. These are also available on the course website, course information website. So you can just refer to these. These are good books and you will find good amount of solving also. Other thing, you can go to some gate books also. They will also have some good questions on Huffman and this kind of things. Even you can search on internet. There are a lot of sample problems available. Okay, if there are no further questions, then you may leave the meeting. I will just end it also from my end. Thank you for attending today's session.